Welcome to day 4. Homework is the day 4 problems in the textbook. And we're just going to go through one by one each of the homework ones and the worked out solutions. So starting with number 1, our expression was continuous. It was positive and it was decreasing, so the integral test applied. So we do our limit as b approaches infinity. Technically, that's a u substitution, but there'd be no correction. So we'd have natural log absolute value of x plus 1, fill in your b, fill in your 1. As b goes to infinity, we get infinity minus natural log of 2, so infinity. So that diverges. Conclusion, we would say that our series diverges by the integral test. Number 3, it is continuous, it is positive, and that's exponential decay, so it's decreasing. So we can do our integral test. Antiderivative, technically, that's a u substitution with a correction of -1. So the antiderivative ends up as negative e to the negative x. When you sub in your b, it's really e to the negative b, so it goes to the denominator. So when b goes to infinity, you'll have -1 over huge things, which goes to 0. So we just have the 1 over e. So therefore, it converges. Remember, the series does not approach 1 over e. Just because we got 1 over e by our improper integral does not mean that is the series value, but it means the integral converges, so the series will also converge by the integral test. For 5, I think this might have been one that we did in class, but this is arctan. It was positive, continuous, and decreasing. When we filled in b as arctan goes to infinity, it approaches pi over 2. So we had pi over 2 minus pi over 4. It was pi over 4 because 45-degree angle, the opposite over the adjacent is 1. And then so we get pi over 4, which means the integral converges. Therefore, our conclusion is the series will converge by the integral test. For 7, it is continuous, it is positive, and it is decreasing. The reason we know it's decreasing is when you go from 3 to 4 in the denominator, that's a bigger jump than natural log of 3 to natural log of 4. So those terms should be getting smaller, and you could always put them in the calculator to see the decimal values too if you're unsure. We want to let u equal the natural log of x plus 1 in this case, because then derivative of stuff over stuff is 1 over x plus 1. So the 1 over x plus 1 dx becomes our du, and we just have u. By subbing in our bounds, the 1 and the b, into the natural log of x plus 1, we get natural log of 2 and natural log of b plus 1. Antiderivative, we have a half u squared. We'll fill in our changed bounds. As b goes to infinity, that first term goes to infinity, so this is a diverges, and our conclusion is that our series that they had given us diverges by the integral test. For 9, we want to let u equal the denominator, the x to the k plus c. The derivative of that exponent comes out front, so k out front, exponent goes down 1 to k minus 1. We got a x to the k minus 1, we just got to correct by multiplying by 1 over k. Well, now this is a 1 over u. And for some reason here, I'm not sure why, I didn't change my bounds. So I had to later on, after I did my antiderivative, I had to put the x to the k plus c back in for u because I didn't change my bounds. You could have changed your bounds to be c, 1 plus c for the bottom and b to the k plus c for the top, and then you could have just subbed in when we had natural log of u. So you would have ended up with the same thing. But anyways, b goes to infinity. Looks like I'm missing, nope, I don't need a parenthesis there. I'm missing my parenthesis here. But because we've got the infinity, this is going to diverge, so our conclusion would be that our series diverges by the integral test. For 11, pretty basic antiderivative. When you sub in your b and your 1, as b goes to infinity, that first fraction is going to go to 0, so we get a half. Remember, that doesn't mean the series approaches a half, just that we have a converge, so our conclusion is the series converges by the integral test. 29, we would want to let u equal the natural log of x in this case. So du is 1 over x dx. So we end up with u to the negative p. So our exponent goes up 1, and we divide out front by negative p plus 1. I changed my bounds here, natural log of 2 and natural log of b. So when we fill those in, the question wants to know what values of p will make this converge. So we want to focus right here. For this to converge, we need that natural log of b to move to the denominator. For it to move to the denominator, we need the exponent to be negative. So we want to consider what values of p do we need for negative p plus 1 to be negative, or in other words, less than 0. Well, when you add the p over, that's p greater than 0. For 33, continuous, positive, and decreasing, technically that's a u substitution, but with a leading coefficient of 1, there's no correction. So we get our natural log absolute value. When you fill in your b's and go to infinity, you end up diverging by the integral test. Now we're going to see in class today, we could rewrite this as the harmonic series. And the harmonic series is something that we briefly talked about last class, diverging, and we're going to see again to show that it diverges. And we'll show you in the notes today how we can rewrite that to show it's harmonic. All right, for 37, we wanted the 6 partial sum. So just in the calculator, you're doing your summation button, 1 to 6 of 1 over n to the 4th, and we get that fraction, or to 3 decimal places. And then we want to approximate the remainder, so we do the integral from 6 to infinity, because we had done the sum out to 6 terms. Go through, do your same process. b is going to infinity, wipes out the first fraction, so we just get 1 over 648. So we're guaranteed that the 6 partial sum is within 1 over 648 of the infinite sum. Now in 43, we don't know how many terms to go out for the partial sum. We want our partial sum, though, to be within 0.001 of the infinite sum. So we're going to kind of do like the process we just did, but instead of 6 to b, we're just going to do n to b, because we don't know how far out we have to go. So we do our antiderivative, we fill in the b, we fill in the n. As b goes to infinity, the first term goes away. And then we've just got an inequality in terms of n, because we want that remainder to stay less than or equal to 0.001. Well, 0.001 is 1 over 1,000. So I multiplied the 1,000 over on the left and n cubed over on the right. Now, those both had to be positive, so the sign didn't change. But also keep in mind, when we're solving this, n's got to be bigger than something. So we don't have to be too careful with our inequalities, because we know in the end it's got to be n greater than or equal to something. So take the cubed root of both sides. Cubed root of that is 6.934. Well, if n has got to be greater than or equal to 6.934, n is only positive integers, because it's telling us our term numbers. So really, n had to be greater than or equal to 7. And the last couple, we're doing the same thing, different function, but we wanted to stay within 0.001, so do the integral of n to b. Your antiderivative would need a correction of negative 1/5. Fill in your b and your n. That first term, as b goes to infinity, that's going to go to 0, because that's exponential decay. And then from there, multiply the 5 over, switch to log form, and then divide over the negative 5. When you put that in the calculator, that's 1.060. We need n to be greater than or equal to that, so that really n has to be greater than or equal to 2 to stay within. And the last one, same idea, but we have an arctan, so fill in your b, fill in your n. Arctan, as b goes to infinity, we've seen a few times as pi over 2. Subtract. You can do a couple different ways. I chose to subtract the 0.001 over to the left, add the arctan over to the right, and gives you that new inequality here. Then undoing an arctan is just doing a tan, so n is greater than or equal to tan of that number. When you put that in, you get that 999.9996 number, so n has to stay greater than or equal to 1,000 terms. We will see in this unit, we'll see 3 total ways to do a remainder. Integral remainder is one of those ways. All right, so we're going to go over to our notes packets in the day 4 portion of the lesson. And today we're going to look at p-series. Well, a p-series is when you have 1 over n raised to some positive number in the denominator. Now, if you had some constant other than 1 in the numerator, that's okay too. You would just pull that constant out front. So like if we had 5 here, we could throw the 5 out front and it would still just be a p-series. So if we see a few of those terms, it's 1 over 1 to raise to whatever p is, plus 1 over 2 raised to whatever p is, 1 over 3 raised to whatever p is, and so forth. And we've got some other examples written out. So the top left one there is when p is a half. The one over on the right is when p is 2. And then the bottom one here, because it's n to the first, is when p is 1. Now that series of 1 over n, that's called the harmonic series. It's going to be a really common one that we will see a lot. And on that series, the reason it's called a harmonic series is in music, if you have a stringed instrument and the strings are all the same material and tension, if the lengths of the strings form a harmonic series, then the strings will produce harmonic tones. So next up, we want to find what's going to make our p-series converge. So we're going to use the integral test to figure that out. First scenario, we're going to see what if p is greater than 0. Well, this is really x to the negative p if we bring it up top. So I'm going to rewrite this as limit as b approaches infinity. We're going to have integral from 1 to b x to the negative p dx. This is going to be similar to one of the ones we saw in the homework. So we'll have limit b approaches infinity. We're going to have x to the negative p plus 1. We'll have 1 over negative p plus 1. And we're going to have our bracket from 1 to b. So we're going to do limit as b approaches infinity. We'll have 1 over minus p plus 1. And I'm just going to leave that out in front. We're going to have b to the minus p plus 1 minus, and 1 raised to any power is just 1. So we want to think about what value of p will we need to make this converge. Well, the scenario we're looking at here is we're going to consider p to be greater than 1. So what we need to imagine is if this p value is anything bigger than 1, it gets negated, and then we are adding 1 to it. So think of like negative 2 plus 1, negative 3 plus 1, negative 4 plus 1. All of those will end up giving us a negative exponent, which will bring b down to the denominator. So this is going to end up as 1 over b to some number, some positive number now. And as b goes to infinity, this term's going to wipe out to give us 0. So because of that, that's going to make this converge. So when p is greater than 0, because it will make the term move to the bottom with a negative exponent, that will make it converge. So far we know p greater than 1 is a converge. Let's look at the next slide, and now let's look at when p is in between 0 and 1. Rather than doing the whole process out, because we're starting the same, I'm going to jump to right here. So we've got limit b approaches infinity. We have 1 over negative p plus 1. We've got b to the negative p plus 1, and then we have minus 1. And the big thing we got to focus on is this term here. If p is between 0 and 1, think 0.25, 0.5, 0.75. When we sub that in for p, negate it, and then add 1, we're going to get a positive exponent. So we're going to end up with b to some number, some positive number I should specify, in the numerator. When b goes to infinity, this is going to go to infinity. So therefore, this case is going to diverge. So we've learned so far between 0 and 1 is a diverge, greater than 1 is a converge. Last case we've got to look at is what if p is equal to exactly 1? Well, if p is equal to exactly 1, just going to rewrite this as our limit quick. If it's equal to exactly 1, this is not a power rule case. This would be a natural log case. So we got limit b approaches infinity, natural log absolute value of x going from 1 to b. So we'll have limit b approaches infinity. We'll have natural log absolute value of b minus 0. And if you visualize the natural log graph in your head for a second, as we go far to the right on that graph, as b goes to infinity, the graph keeps increasing without bound. So this is going to infinity, so this is a diverges. So our overarching question here was under what conditions does a p-series converge? Our conclusion is that a p-series converges if p is greater than 1. And if you want to add here, it doesn't answer the question quite, but that means that it diverges if p is greater than 0 but less than or equal to 1. Now, this series we just looked at, again, is called the harmonic series. So in series form, this would be written as sum n equals 1 to infinity of 1 over n. So that's our harmonic series. When we see that from this point forward, which we'll see it a lot, there are two conclusions you could write for it. We have seen twice now that it diverges, so you could say diverges since harmonic, or you could say diverges p-series where p is greater than 0 but less than or equal to 1. Either of those explanations, the blue or the purple, would be valid for what we're going to have to describe. Okay, it's really just your choice which one you recognize it as the harmonic. We can just say it's the harmonic so it diverges. We've shown that. Or you can do it as a p-series. So that's the big new thing for today, p-series. If you recognize a p-series, just look at that exponent in the denominator. And if it is greater than 1, then we can automatically say it converges by p-series with p greater than 1. If it's a exponent in that denominator between 0 but greater than 0 but less than or equal to 1, we can say it diverges by a p-series. So, looking at some real quick ones, each of these I want to write what the series notation would look like and then write what our conclusion would be. This would be series n equals 1 to infinity. We'd have 1 over n to the 1.2. We would want to recognize, okay, that's a p-series. It's just 1 over n to a positive number. So we would say, because the p is greater than 1, we would say this converges and say p-series with p greater than 1. Our second one in series notation, this would be n equals 1 to infinity. We'd have 1 over n. Cubed root is really raised to the 1/3. This would be a diverges. And our reasoning, we would say, is p-series where p is greater than 0 but less than or equal to 1. Now this last one, this is not a p-series. It would not be the same number raised to different powers in the denominator. This is really, here, this is really 2/16. This is really 4/16. And then this is really 8/16. So what this actually is a geometric series. So in series notation, this would be the sum from n equals 1 to infinity. Our first term is 1/16, and we're just doubling each time. Now, we've just got to be careful of our exponent to make sure that it works out. When we sub in 1, we want it to just be 1/16. So we would want this to be to the n minus 1, so that when we sub in 1, we'll have 2 to the 0, which will give us 1, and just give us 1/16 back. Now, once we have this in series notation, we've got that our r value is 2, so we could say this diverges since geometric, absolute value of r is greater than or equal to 1. If that thing you're multiplying by, if its absolute value is less than 1, that would be a converges. Now the bottom one here, it says verify by the integral test that this converges. If we flip back, I feel like we might have looked at that one on the homework. Here it is right here. Number 11 was that on the homework. So let's just look at this. So we had our 1 over n cubed. We did our antiderivative. Eventually, we had a b squared in the denominator. As b went to infinity, that went to 0. So we got a half, so that converged. Again, with the integral test, it doesn't mean the series is going to a half. It just means the integral converges, so the series also converged. So we're not going to have us redo the integral test, but what I would like to do for that problem is just, what we'll do is we'll just practice how you would probably want to determine this converges. So if you're given this on a homework problem from here on out, probably don't want to do the integral test. That's longer. All we would say is that this converges, and we would just say p series with p greater than 1, and that's it. So p series is a really, really easy one. So it's probably after nth term test and maybe geometric, it might be one of the first few that you want to keep a lookout for. All right, if we go over to our next slide, this series, does it converge, true or false? Well, what we want to notice is we got 1's in our numerator, denominator's just going up by 1 each time. We can actually be kind of slick in how we write this in series notation. We have 1 on top, and what we can actually do is we can make the bottom be n, and just say that n starts at 10,002. And then this is just a harmonic series. So we could say diverges since harmonic, or you could say diverges because it's a p series with p greater than 0, less than or equal to 1. So I guess we should just specify also that the specific question they answered would be false, and then our reasoning is because it diverges since it's harmonic. So with the harmonic, you might be able to rewrite things sometimes to show it's a harmonic. Again, if we had like 7's all on top here, you could just pull the 7 out front and then show that it's harmonic as well. It will still diverge, even if you have some constant you're multiplying by. Now, it's not very intuitive that the harmonic series diverges. But a way to think of it is, if you gave me a positive value, if we add enough terms in the harmonic series, we will eventually get to that value. So what we're going to do is, in our calculator page, we're going to define the harmonic sequence recursively. So if we go to our calculator page, go, sorry, not calculator page, graphs page. And we go to menu, graph entry, edit. If we go to sequence mode. So we're going to put this in as U1 parentheses n minus 1. That's like saying a to the n minus 1 or the previous term. And then you're going to add on 1 divided by n. And then our initial term, we would be putting 1 in. So 1 over 1 is just 1. So we're going to go to a control T. And let's just check to see if this makes sense. In the harmonic series, the first term should be 1 over 1. So we get a sum of 1. The second term is 1 over 2, or in other words, a half. So 2, notice, adds up the first 2 terms there. So in our chart here, we're letting m be our sum. And we want to see how many terms do we need to add to get to each of these things. Well, to get to 2, it looks like we've got to go to 4 terms to get there. To get to 4, if we scroll down a ways, we're getting closer. Looks like we got to go to 31 terms to get to 4. Say we wanted to see, does our series eventually add to 6? Well, it might take a while. Still not there yet. Oh, there it was. Looks like it's 227. So 227 terms to get to 6. Say, hypothetically, we want to get to 18. It might take a while to scroll there, but it'll eventually get there. So no matter a positive value you tell me, we can go out to enough terms by adding terms on in the harmonic series, and we will eventually get to that. So that's just kind of a rough way to wrap your head around that, yes, it does actually diverge because we will eventually add up to every single possible number you could throw at us. All right, one last one for this video. We want to know, does this converge or diverge? And what I want to model on this problem is we've now got a bunch of different tools, and the question often becomes, well, which ones should we try and use? So I want to model kind of the checklist you want to go through. One of the easiest ones at the start is the nth term test. The nth term test, we want to think as n goes to infinity, do the individual terms go to 0? If that is not true, then it automatically diverges. If the terms do go to 0, then we just need to find another test. We can't make any conclusion. Well, denominator is going to get big, numerator is going to stay at 1, so as n goes to infinity, this will approach 0, so can't use the nth term test. This can't use that to show it diverges. Another easy one early on that we know is geometric. Geometric would have to show repeated multiplication. It would look exponential. You would have stuff raised to a power. We don't have that here, so this is not geometric. The next early easy one to look for is p-series. Well, p-series is just 1 over n raised to positive numbers. The natural log n throws that off, so this is not a p-series. Next, of our ones that we have, maybe look for telescoping. For telescoping, we need 2 fractions, or 2 separate terms, I should say. Most frequently they're fractions, where we're subtracting them. Because we've got that natural log of n, this wouldn't be able to be split into partial fractions like we could if it was a polynomial. So no for that. So the only thing we've got left is our integral test. Now, before we do it, we should check to make sure it's always positive. And we're starting with n equals 3, so that'll make sure that the natural log is positive, so that's good. It should be continuous. There's no problems anywhere from 3 on. And it should be decreasing, and we saw from the nth term test that it would be decreasing. So this allows us to do our integral test. I'm going to jump right to the limit and have limit b approaches infinity. Integral, we're doing 3 to infinity in this case because we started at 3 of 1 over x natural log of x dx. We would want u to equal natural log of x. So du would be the 1 over x dx, and we've got a perfect match. The natural log of x is in the denominator. So we're going to have 1 over u du. And if we redefine our bounds, we'll have natural log of 3 and natural log of b. So we'll have limit as b approaches infinity. This is going to be natural log absolute value of u being evaluated from natural log of 3 to natural log of b. That's going to give us limit b approaches infinity, natural log of b, minus natural log of 3. Well, natural log of b goes to infinity. When natural log goes to infinity, that also goes to infinity. So we'll have infinity minus natural log of 3. Because we've got that infinity there, this is going to infinity. So we would say this is going to diverge. Because the integral diverges, we can now say that our series n equals 3 to infinity of 1 over n natural log of n diverges by the integral test. So when you're given problems on homework, on the tests, where it doesn't say specifically that a certain test has to be used, what we demonstrated up here is probably the checklist you want to go through of what we have currently. Check for nth term. If the terms don't go to 0, then you can automatically say diverges by nth term test. Check for geometric, that's repeated multiplication. Check for p-series. All 3 of those first ones really easy. Telescoping, look for, to be honest, telescoping is going to be, once we have all of our tools, one of the most rare ones we'll see. But look for that. And then integral is towards the end too, just because that's a lot of work. Any time left in the period you can use to start the homework or work on problem set, and have a great rest of your day.